Hey everyone, welcome back again to the YouTube Academic Project Series. I am Rohan, and in this video, we are going to go through the rooftop solar panel detection using deep learning. And the project ID is this, and the project name is this, which we'll be basically using while submitting the task that we are going to give you at the end of this notebook. And for those who are new to this YouTube Academic Project Series that we have started at Spartificial, you must know that if you're going to complete the task that we are having at the end of this notebook, you will be getting certificate based on how you are going to perform in it. So yeah, for more information, please stick by the end of this video. You will be getting all the information as in how you can stand a chance to win certificate if you are going to submit all the tasks and if you are doing it properly. So now let us understand the workflow of this notebook. We are going to start with the introduction to the problem, as in what is the problem that we are going to deal with, then what is the data set that we are dealing with, and then import some of the necessary libraries and the modules for this notebook that we are going to use throughout this project. Then start with some exploratory analysis and scale the data or the images that we are having. And then we'll build our CNN model and evaluate the process and show you the results. And there will be at the end some task for you. In this particular project, we are only having one task for you. And let's see how you're going to do it. So now moving on towards the introduction to the problem. So why should solar panels be detected? So presently 1% of the electricity produced worldwide comes from solar energy. In fact, predictions for solar energy production indicates a possible 65-fold increase in output by 2050, making solar energy one of the world's greatest source of energy at that point of time. And 30% of this energy is thought to be produced by solar photovoltaic or solar PV, basically the power systems mounted on the rooftops. So solar PV power has already started to take on a more and a bigger part in the generation of electricity in the US in the recent years. And the solar energy production has increased by approximately 75,000 gigawatt hours or 39 times between the 2008 to 2017 or 2008 and 2017, or a 39-fold increase, whatever you want to call. That's the amount of increase of the solar energy production that we are seeing. And here's the overall view on the global growth. So we are having different continents over here and different countries, and based on all the growth that we are seeing over here from 2010 till 2030, like this is the expected, the prediction, as I had talked about it over here, the predictions over here. Yes. So these are the kind of trend that we are able to see year by year, as in the global PV installation estimate, as we can see says that the granular data on distributed rooftop solar PV is becoming increasingly important as solar photovoltaic or PV becomes a significant segment of the energy industry. An imagery based solar panel recognition algorithm that can be used to create detailed databases of installations and their power capacity would become extremely helpful to solar power suppliers and consumers, urban planners, grid system operators, and energy policy makers. The fact that the solar panel installers typically keep installation details to themselves is another factor in solar panel detection. A well known solar panel detection technique or algorithm is therefore urgently needed. However, there hasn't been much effort done to identify in aerial or satellite photographs. We first require a labeled dataset of satellite images in order to create an algorithm that can recognize solar panels from aerial or satellite imagery. And that's exactly what we are going to do in this project. And now let's just go ahead and understand this dataset and how are we going to use it for our particular project. So in the first few images, we can see that there are some kind of different orientations. We are having solar panels on different background. We are having solar panels, and in the second row, basically we are having no solar panels. But yes, the images are pretty much similar as we can see. And now our goal is, no matter whatever is the orientation, whatever is the background, we have to make sure that if we are passing this kind of image into our model, that model should be able to classify if that image is containing any solar panels or not. So that's the main goal, and this is the kind of data set that we are going to deal with. And now if you go ahead, let's just start by importing all the necessary libraries or the modules for this notebook. So we are starting with the data handling and linear algebra, that is nothing but the numpy and pandas. And now moving on towards the visualization part. So we are basically importing all these libraries. The main ones are the matplotlib and the seaborn. We are just using this in order to create different figures, different plots, customizing them, then read the images that we are having in the data set. So all that purposes will be fulfilled with the help of these libraries. And then moving on towards the data analysis part. So from sklearn model selection, we are importing stratified k-fold. Basically, you will understand this while we are implementing this. And if you have already looked into our previous YT academic project series, some of the projects are out of it, then you must have noticed that we have already used ROC curve and ROC AUC score. But just don't worry if you're even watching it for the first time. I'll just explain it in a way that you'll be understanding everything. And similarly, one last metric that we are importing is basically the confusion matrix. And then we're just importing different layers from Keras for building a convolutional neural network. And for this particular project, we're going to build a CNN. So rather than importing all the layers with the help of keras.layers every time, we are just importing it all together once over here so that we can just directly call this convolution 2D or dance or whatever layer that we're going to use. And because we're going to build a sequential model, so I'm also importing from keras.models import sequential. So that's the basic idea about what are the libraries that we are importing over here. And now let's just move ahead and start by importing Google Drive for the dataset access. So the first step is basically to download this particular dataset. If you just click on this particular link, it will redirect to a Google Drive folder named as data. You first download that to your system and then again upload it to your main drive. You just go to your Google Drive, go to the main page or my drive particular folder, and then you just paste this or upload this folder over there. Because if you don't do this particular step in this way, then you will have to manually change the path for the training images as well as the training labels. So just in case if you don't want to create this kind of a hustle for you, so the basic idea is download this folder named as data inside this particular link. And after downloading that, upload it to your own drive, my drive folder. And yeah, that's it. After that, you can just use the same link or the same path that we have provided in this particular notebook. So after this particular step is done, the next step is to mount your Google Drive. So this basically means we are connecting your Google Colab with your Google Drive. So that's how we are going to do it from google.colab import drive. And then this particular code is just going to mount your Google Drive on the Google Colab. And after that, as I had mentioned, these links are not going to work or the paths are not going to work if you have not done this step properly. So make sure that you are placing this data folder into your main drive or your my drive particular page. And after that, so we are having this variable named as dir underscore train underscore images and dir train labels for the respective images in the training dataset as well as the labels in the training dataset. So these are the things that we are going to use in this particular notebook. And there is also one more folder named as test. You can just choose to ignore that completely and just call this training dataset, that is your training images as well as the labels of the training. All right, so now the next step is to simply go ahead and look into what are the kind of details or the things that we are having inside both of these files. So training folder is nothing but a folder inside which we are having a different images to train, and the labels underscore training.csv will have something. So let's just go ahead and do some exploratory analysis and then scale the images that we are having inside the training folder. So let's just go to that particular part now. So I'm using a read underscore CSV method of pandas and passing my dir underscore train underscore labels variable that we have defined for this particular path. And that's the beauty. We are not just going to copy paste this again and again whenever you want to use this particular path. We are just going to call this particular variable that we have defined. So that's the beauty of that, as I mentioned. So I'm using this particular thing inside this read underscore CSV and I'm just visualizing the first 5 data points inside this dir underscore train underscore labels or the CSV file. So for that, I'm just using dot head. So we can see these are the first 5 points that we are having with respective IDs and the labels. So ID are nothing but the names of the image before TIF. So all the images that we are having, as I mentioned earlier, is .tif format. So the name of the images are contained in a way 0.tif, 1.tif, 2.tif. That's what this means. And label is nothing but it is containing two different values, 0 and 1. Where 0 means that the image is not containing any kind of solar panels, and 1 simply means that the image is containing some kind of solar panels. So that's the basic idea inside, what is the content inside the CSV file. And then now we are going to create a function in order to load the data from the training folder and pre-process it. So now let's go ahead and define our function load underscore data. It's going to take in two different input parameters. One is the data directory. It's nothing but the training folder, the path that we had created or the variable that we had created for the training folder, inside which there are different images with different unique IDs like 0, 1, 2, 3. And we also know that the images are in the .tif format. So this is nothing but a folder inside which there are all the images that we are going to deal with in this project. And over here, the second parameter is nothing but the respective labels. We had also just seen the CSV file over here, right? So we are going to just import both of this over here as the input arguments. And the main idea of this function, the main idea is just to go ahead and extract all these images and convert it into its respective NumPy array format. And along with that, whatever is the unique image IDs that we are having, we are also extracting, while we are extracting the images into converting into the NumPy array, at the same time we are also extracting the labels with that particular unique ID. So we are going to do that at the same time with the help of for loop. So how are we going to do that? Let's just look into it. So first of all, we are using again the read underscore CSV particular method of pandas to read the CSV file. And inside the CSV file, we know that there are two different columns, ID and label. So what we are doing is we are first of all extracting all the IDs. So inside this data frame that we have created, labels underscore PD, inside that there is a column named as ID. I want to grab all the values of it. So I'm just grabbing them and storing it inside this IDs. And then I'm creating the empty list. And this is the list where all the arrays are going to be stored, where we are going to convert the images into its respective array. We are going to save it inside this particular list named as data. So what we are doing now is, inside all the IDs that we are having, we are just naming it as the identifier. So for all the identifiers inside these IDs that we have created, we want to create a file name. So inside that file name, we are passing the directory of the training folder. So inside the training folder, if you see, we are having this kind of a slash at the end. So after that, the file name will be like, slash 0.tif, slash 1.tif, slash 2.tif, and so on and so forth. So we are already having that slash. So after that slash, if I want to open the first image, that is 0.tif, what I should do is I should pass the unique identifier, that is the first one, that is 0. If you can see, the IDs are already in the ascending format, 0, 1, 2, 3, 4, and so on and so forth. So if I want to take these images as 0.tif, 1.tif, and for that I'm using this for loop. So this data directory is the training particular path that we are having, the folder that we are having for the training. Then we are adding this identifier and we are converting that into the string, because we are again having the string format. The training path is in the string format. So we need to convert that particular identifier also into the string format, or else it's just going to throw some kind of an error. So after that, we are also adding plus .tif, because we know that the file, the complete name of the file will be 0.tif or 1.tif. So for every for loop, this identifier is just going to take different IDs and create different file names for it. And now I'm using the matplotlib, that is the MPL that we had imported earlier. From that, we are using image.imread to read that file name and convert basically it into the NumPy array. So all the images, once the file name is generated, I am passing it inside this particular thing, and it's going to give me the respective array of that image. And then I'm just saving that array inside this particular list by appending that array inside this list that we had created earlier for the data. And this process is just going to repeat for all the IDs that we are having inside that CSV file. So basically, we are just converting all the images into its NumPy array format and saving it inside the list of data. And now, just to handle the data set in much more efficient way, what we are going to do is we are going to convert this list of data into the array of data. So right now what we are having is we are having a one whole list inside which we are having different bunch of arrays which represents the images in its NumPy array format. So now we are just going to convert this list into the array. And how are we going to do that? So we are passing this np.array onto the data list. So now that's how we are going to convert that list into the array. So now we are having one whole array inside which we are having different arrays. And we are obviously going to just return this as the output of this particular function. And along with that, so let's say that we are having the first array. What is that first array representing? That array is simply representing the NumPy array of that 0.tif particular file. So now we have to also extract the respective labels with it. So we already know that for respective IDs, we are having its label. So for 0.tif, the label was 0. It means it does not contain any kind of solar panels. For 1, again, no solar panels. For 2, there is a solar panel. At least one solar panel is there. And then for 3, again, there is at least one solar panel in that image. So what we are going to do is, because we have already taken out the arrays of different files from the training data, the respective label is just next to it. So like, the basic idea over here is to extract all these labels in this particular format without changing it, just like we did for the IDs. So for that, what we are going to do is we are going to take this labels underscore pd, that data frame that we had created earlier. We are going to take the label column and extract all the values as it is without manipulating it, because the order is just the same. So we don't need to manipulate it. And again, we are going to pass that as our output of this particular function. So as I mentioned, the first array inside that whole long array of data contains the respective labels in the labels particular output. So that's the whole idea that we have created inside this particular function. And now let's just go ahead and call this function on the actual training folder as well as the respective CSV file and create the respective X and Y data. So X data, again, as we know, it's nothing but this data that we had talked about, and Y is nothing but this labels that we had talked about. So you'll be understanding, like, what are the exact contents inside this in the next coding cell. So what we are doing is we are displaying all the images with and without the solar panels with the help of this X and Y. So what we are doing first of all over here is, so I'm simply going ahead and creating these subplots of first 6 images that we are having inside the training folder. So how am I doing it? I'm not going ahead and calling directly from that particular training folder. Instead of that, what I am doing is, because I've already created this arrays of the different images, we are just going to use that arrays and convert that into the images with the help of .imshow function inside the PLT. So that's the basic idea. And then I'm just going to give a title to it in a way that, because I already know that x0 is a particular array of an image and its respective label is stored in y. So now if that label is 0, I want to give a title of no solar panels in the image. And if the title is not 0, that means that is only one possibility, right? The labels were either 0 and 1. So if it's not 0, I want to have my title as solar panels in this image, because 1 basically means that, yeah, there are at least one solar panel in this image, right? So that's what I'm doing over here. So how exactly I'm doing it? Because I want to plot the first 6 images, that is from the ID 0 till the ID 5. So I am using the for loop going from the value of 0 till 5 with the help of this range function. That is, this 6 basically means I'm taking the values from 0 to 5. And then I'm creating the subplot with 2 different columns and 3 rows. And this is nothing but the position where I want to create the respective figure. So when the value of I will be 0, this will be 0 plus 1. That is the first position. This is this position. Then when the value of I will become 1, so 1 plus 1 is 2. That's the second position. So on the second position, I'll be getting the second figure. So like that, I'm creating the subplot, and the respective figure that I want to plot, what I'm doing is I'm going inside that array. So x0 basically means the first array which is representing the first image of the training folder. So I'm simply displaying that particular array with the help of plt.imshow, and then I'm also adding a title to it. So if the respective label is 0, this is the title, or else this is the title. So again, to show the title, I'm using this plt.title command, where this is the title that I'm setting. The color is red. I'm just setting the weight of this fonts to bold. And then this tight layout is nothing but, like, if I'm not going to use this tight layout, the spacing between these images will not be in this particular way. You will either have to manually adjust it with the help of a different command named as plt.adjust subplots. But again, that's not something that I prefer, and that's why I've used tight underscore layout, because it's doing a pretty much good job. So I'm just using that particular function, and then I'm just displaying all these images without any kind of text written over here. So if I don't write this plt.show over here in the Google Colab, it's going to give me some kind of outputs of titles and the position of these subplots and all that stuff, which I don't want to see. And hence I'm using this particular command. But even if you don't use it, you will still be able to get these images. So now let's just look into the first image. So this is nothing but 0.tif. And because we know that 0 and 1, the both of the images were not having solar panels in it, because if you just look into these labels, so in this first 2 IDs there are no solar panels, but then in the next 3 images there are solar panels. So let's just confirm if this kind of thing has been properly done or not with the help of the function that we had created over here. So the first 2 is not having any solar panels, and the next 3 are having solar panels. Yes, so this is done in a proper way. That's what we can see. And just to confirm, in this image, yes, there are no solar panels. Over here also there are no solar panels. Over here there is. Over here also there is. Here also there is. And over here there is no solar panel. Don't just get confused with the shadow. Okay, this is the shadow. This is not the solar panel. Okay, this is the shadow. And therefore there are no solar panels in the 6th image as well. So yeah, that's the basic idea that we have created, that yes, this load data is working really very well and we have just visualized it in a proper way. And I just hope that you all are understanding what I'm explaining over here. The coding part as well as the just the part that I'm just explaining orally. I hope you are able to get all of it. Just in case if you are not able to get any kind of concept or the thing inside the coding, you are free to ask any kind of questions in the comment section of this particular video. Alright, I'll just reply to you as soon as I can. So now moving on towards printing the shape of the data set. So what we are going to do is we are going to print the shape of that X. Remember, X is nothing but the whole array. That list that we are having initially in that function, we had converted that into the array, right? So this X is containing all the bunch of different arrays that we had converted from the respective images. So if we are looking into this shape, x dot shape is going to give you the whole shape of that X array that we have created. So it contains total of 1500 different arrays of each having the shape of 101 cross 101 cross 3. So there are total of different 1500 arrays inside one whole long X array, and each of the shape of that array is 101 cross 101, and obviously because it is the RGB format, we are having three channels. So that's a basic shape that we are having. And then as I mentioned, the same thing is written over here. Now, if we are looking at the distribution of Y, how many images are containing no solar panels and how many are containing at least one solar panel. So the distribution is in a way that there are 995 images with a zero label, which are not having any kind of solar panels, and 505 images, 505 images are containing solar panels, at least one solar panel. So that's the idea behind the distribution of y, and how did we got it? With the help of numpy.bin count. So this bin count is just nothing but the binary count inside that y. So inside y there are two different values, 0 or 1. So what are the total counts of 0 and what are the total counts of 1? So 0 are 995 and the 1 are 505. So that's how we are getting this particular output. And now you might be wondering that we are just dealing with 1500 images. So is it enough? So obviously you will understand this answer, like this one of the tasks that you have to do at the end of the project. But I'll just give you a basic hint. If you think that this data set or like this kind of thing is pretty much less, the amount of data that we are dealing with is pretty much less. So how you can increase it? The idea is the data augmentation. And that is nothing but we are going to change this image into multiple different ways. You can create some kind of rotation over here to the images, add some kind of flips to the images vertically, we can flip it, or the horizontally, or add some kind of different brightness, or we can do a bunch of different augmentations. You just need to go out and read about how I can create data augmentation on images for the CNN or something like that. You just try to do some kind of research if you don't already know how to do it. And this is one of the tasks that you're going to do. You're going to augment the data and then you're going to compare it with the result that we have obtained in this particular project. So now let's just go ahead and move on and look, in the last step that we are doing inside this part is scaling the data. So the original data that we are having is containing multiple different colors, and based on this the amount of pixel values are just going to change in between 0 to 255, right? So 0 basically means dark, 255 basically means white. So we are having all the colors in between them with different pixel values. So now instead of that, what we are going to do is we are going to convert it into a particular range from 0 to 1. So what's going to happen with the help of the scaling of the data? Our machine is going to understand very smoothly and efficiently, okay, this is the kind of pixel that I'm dealing with. So that's the way. In order for your machine to process the data in a much more smoother way, we are doing the scaling part. So instead of dealing with a range of different values from 0 to 255, we are just scaling it down to 0 and 1. And how are you going to do it? We are taking the respective uh, pixel value in the data and just dividing that with 255. So the maximum value we already know is 255. So 255 by 255 is going to become 1. And all the values apart from 255 are less than 255. So anything we are going to divide that with 255 obviously will be less than 0. So all the values will be in between either 0 and 1. When will it be 0? When the value of x itself is 0. Wherever there will be extreme black spot in the image, the value of that particular pixel will become 0. So 0 over 255 will again become 0. So that's how we are scaling down the values of all the pixels from 0 to 255 to 0 to 1 in order for our machine to understand this in much more smoother way or an efficient way. And now we move on towards creating the convolutional neural network model. But now, what if we are completely new to the concept of CNN? So, we have already covered this whole concept in one of the project named as ship detection using the satellite images. It is a whole project of about 3 hours long, where we have explained everything from scratch related to a convolutional neural network. What are some different layers that are present? The the usual layers. We have explained them in detail. Along with that, how are we going to implement it in a unit architecture? Where unit architecture is nothing but a way in which different layers are arranged of convolutional neural network. So you can just go through it. I'll just pin that particular link inside the description of this video, but you can just go through it and have a proper base if you're looking it for the first time. However, I'm just going to give you an overview of what is a CNN very quickly. So CNN basically are used for this image kind of data, where we are taking these images and passing different filters onto these images one by one. It keeps on going like this, and these filters are just going to learn the pattern of the images that are present inside this image. So these patterns are once recognized, can be then later used to identify if this particular image was containing a truck, if it was containing a car, or similar to our particular data set, is it containing any kind of a solar panel. So we are training our model in a way that we are going to take some different bunch of filters, we are going to pass it inside this particular fashion, and that CNN, this whole model that we'll be creating, will be able to understand that okay, in all the images when we are having this kind of feature, where we are having some kind of square kind of thing, some kind of this color kind of thing, then it is belonging to the solar panel, and therefore it will just give the ID or the label of 1. For that particular ID, we'll be getting the respective label as 1. So we are going to train our model in a way to learn from the existing data, and then we are going to use some kind of a cross validation technique in order to test how we are going to perform this particular thing. So I'll again explain this in much more detail a bit later. But the basic idea of CNN is to just identify different patterns over here inside an image, and then classify it, segment it, and do all the kind of different stuff that is possible with the help of CNN. So for our use case, we are just going to classify with the help of the CNN if this image that we are passing inside the model is containing any kind of solar panel in it or not at all. So that's the basic idea. All right. So now let's just move ahead, and obviously you can go ahead and read this kind of thing along with the link that I'm going to provide in the description of this video. You can also go to that video as well. That's an amazing whole project where we are covering how you can detect ships from the image from the satellite. How are you going to detect ships, how many ships are there, and all that kind of stuff is basically explained over there. So that's a particularly very brilliant project. If you're just going to look into it, just do it very properly. And yeah, moving on towards building the model of CNN. So we already know that we are going to define the function named as build underscore model, and it's simply going to return you the Keras model of CNN. We are going to use layers from Keras, right? I told you while importing all the different layers. So that's what we're going to do. We already know that all the images that we are having the shape of 101 cross 101 cross 3. So that's the input shape that we are having, that we are going to pass inside the first layer of convolution. All right. So because we are going to create a sequential model where we are going to add all the layers in sequential way, the first layer, then the second layer, then the third layer, we are going to keep on adding this kind of layers. So yeah, we are using the sequential model. And again, you can go through all these different comments that we have written over here in order for you to understand it in much more better way of what we are doing. But the basic idea is we are first of all creating the convolution 2D layer with 32 different filters and the kernel size. This kernel size is nothing but the filter size. What are the filter that we are creating? What's the dimension of that one particular filter? So we are creating a 3 cross 3 filter. It's just going to move 1 unit to the right, then again come down, move towards right. In similar way, it's going to detect some kind of features in it, and we are using the activation function as ReLU, because remember, sigma is one function, or the tanh kind of activation functions are usually going to face the vanishing gradient issue. So to avoid that, we are basically using ReLU. That's the popular activation function to use in any kind of neural networks to avoid this vanishing gradient problems. And the input shape it's going to take is basically the one that we have defined over here, 101, 101, and 3. So that's what we are passing in the first layer. So after that, we are going to get one another output from this particular image, which will again be of less size as compared to what it was originally. So originally it was 101 cross 101 cross 3. Now it will change to some different dimension because now we are reducing the size of the images. Because see, what's happening over here is once you are taking all the see, the convolution happens in a way that if you are passing a filter over here, it's going to do the multiplications of the arrays over there and create one single value. So that's why the overall shape, like this whole bunch of 3 cross 3 pixels, are going to be converted to only one single pixel in the output image. So the overall image, as you can see, it's just decreasing as we go ahead, right? So that's the basic idea. So we are decreasing the shape of the image, and then after that, once we are just having the important features inside that particular, we have grabbed the important features from that image, we are adding the batch normalization layer. It is basically used to improve the speed of the training. And how it does so, it basically normalizes, like after we are getting an output, again the output will be getting will be having some different range of values. The pixels will be of some different range. So again we are concentrating it into some particular range, and after that again we are moving ahead. So it allows you to, like, improve the speed of the training. It also allows us to use the higher value of learning rate so that we are able to reach the convergence very fast. So that's the basic idea of why do we use the batch normalization layer over here. And then again, now if we keep on moving ahead, you will see that we are just using some different number of filters with the same kernel size, same activation. And again, then we are adding this batch normalization layer. So after each and every convolution layer, we are just adding this batch normalization layer just to improve the speed of the training basically. So we are doing it again for the layer 3, and then we see something really very different. That is the max pooling 2D layer. Now the purpose of the max pooling 2D layer is whatever is the output that we get after the convolution layer, now we are still going to decrease the image shape and only grab the maximum value of the pixel. So the feature that is most prominent inside the overall output that we got from the convolution layer, now just grab only that part and give me the output of it. So that's what is going to be taken care with the help of the max pooling 2D layer. Then again, we are having some bunch of convolution layers, and then again a convolution. I mean, after the convolution, we are again having the max pooling, and this keeps on going until we are reaching at the second last layer. That is the global max pooling 2D layer. So basically, see, there are two reasons why we use the global max pooling 2D. If I just go up, now in order to get the output, now in order to first of all get the output, what we need to do before that is we need to convert this 2D outputs into a one-dimensional array, and then we can map it to the different output. So now in order to map this 2D into a 1D array, what we can do is you can either use the flatten layer to just flatten all this 2D into 1D array, or else you can use the global max or global average pooling layer as well. So what we are using is the global max pooling layer. So what it's going to do is the final output that we are having before we flatten it, it's simply going to again pass the filter, and again from that filter, what is the maximum value, it's going to take that value and just pass it over here. Then the filter will again move towards right, and it will again take the maximum value and write it over here. So that's how you're going to convert the two-dimensional array into the one-dimensional array. With again you are giving the like you are downsampling again your image in a way that again you are getting the most prominent features out of this last particular 2D array that you are getting out of all this convolution and the max pooling layers that we had used. So that's how we are going to flatten with the help of the global max pooling 2D. If we are using global average pooling 2D, it's simply going to, rather than taking the maximum value, we are going to take the average value of out of that particular filter. Like when we are passing that filter onto that particular image, it's going to take the average value of it rather than the maximum value. So you can either try to use that as well, or you can, like, just continue with the max pooling 2D, whatever suits you the best. You can also go ahead and try, like, just don't downsample the image, keep the number of uh, values that we are having, the number of pixels that we are having, we don't want to change that. We just want to keep it as it is and just flatten it as it is. So you can also go ahead and try to use the flatten layer for that. But anyway, at the end, after this particular layer, the last layer that we are having is the output layer. Once we have converted it into this particular flattened layer, we are just simply now mapping. Like, see over here, what we are having is we are having one extra dense or the hidden layer. Now it's up to you. If you want to create a much more deeper network, you can add multiple hidden layers or the dense layers. But what we are doing over here is, after flattening it with the help of the global max 2D layer, we are just mapping it to the output layer. Now that output layer is going to have only one neuron. either that one neuron will be of class 0 or of class 1. So whatever it is, we know that because it's a binary classification task, now the activation over here is going to come change to sigmoid, because now sigmoid is the widely used activation function for the binary classification, for the classification layer, the last layer that we are having, the output layer. We always used sigmoid if there are binary classification tasks, but if you are using multiple classification, like multi-class classification task, at that time we use the activation function of the softmax. So sigmoid basically gives you the probability of the output of 0 and 1. So the one with the maximum probability will be assigned as that particular label. So let's say for the first particular image that I'm passing, and that is giving me the probability of 0 more as compared to 1, then it basically means that I'm classifying this image with the label 0. It means it is not having any kind of a solar panel in it. So that's how we are defining our output. And now we can simply move towards the compilation of the model with the help of model.compile, and the optimizer that we are using in order to get the optimal parameters in the best possible way with the help of the Adam optimizer, and the loss that we are using, where loss is nothing but the updation will be stopped when the parameters are just not updating. That means when the loss becomes 0. So the loss function that we are choosing is the binary cross entropy, because we are dealing with the binary classification task. And the matrix that we are using over here is the accuracy. Again, accuracy is not the perfect matrix to be used while dealing with the imbalance in the data set. We know that the number of zeros are greater as compared to ones, almost 50% times the data set is more, because 9 and 5 data are for the 0 label and only 500 something are for the one label. So matrix accuracy is not the best one. The reason that we are using it, you will understand it in a while. Okay, and that's how we are returning the model by creating it. So we have created the whole bunch of CNN model with different convolution layer, batch normalization layer, max pooling layer, and multiple stack of it on one top of the other, finally flattening it with the help of global max pooling 2D, and then we are getting this output. So that's how you're going to create your model. And then now we can move on for the checking of the performance of our CNN model, as in how is it performing. And the technique that we are going to use is the stratified k-fold cross-validation technique. So in order to first of all understand the cross-validation, what happens over there is we take one whole data set that we are having and create multiple subsets of this data. And in all of these subsets, we are going to split the data into the training part and the validation part. So now we are going to train that training part and then just validate it right away on that particular subset that we have created. And then we just repeat this step for the multiple data set that we have created, or the subset of the data set that we have created. So now that's what basically an idea of the cross validation. Now what happens inside the stratified k-fold cross validation is, now this we use for the imbalance in the data set. So the stratified version of the cross validation is, while we are creating the subset of this data set, it will be created in a way that in each split that we are having, there will be almost equal likely chances of zeros and the ones. Like we are trying to create the balance in this subset of the data set that we are trying to create. So we'll be getting majority of the splits in a way that it will be having this proper balance, some kind of somewhere near balance of the data set as compared to what we are having initially. That's the purpose of using the stratified k-fold. So now let's just go ahead and rate this particular function that we are having in front of us. So CV performance assessment, where x and y are nothing but x is the data of the array that we have created, y is the respective labels. This num folds is nothing but the number of splits that we want to create. CLF is the model that we have created for the CNN. CLF is nothing but the classifier, and the random set. See, now when we are going to create this subset of the data set, it's always going to happen randomly. So now in order to create that same kind of randomness every time we run this code, we need to have some kind of a seed value, which will make sure this randomness is always going to be same whenever we are running this. And we are setting it to the value of 1. You can set it to some different value. But yeah, we need to ensure that we will always get same kind of randomness. So that's what we are going to take care with the help of the random seed that is set to 1 in this case. So now as I mentioned, we are going to divide this training data into k different folds or different subsets of training and validation data. And for each fold, the classifier will be trained on the training data and will be tested on the validation data. And then the classifier prediction scores are aggregated, and that's what we get as the output. So now we are just creating the prediction scores over here. and the prediction class is over here. But to be honest, we don't really need the prediction class over here because it's nothing but the scores that we'll be getting. If the threshold we are setting it to 0.5, anything that is greater than 0.5, we call it as a class 1, and everything apart from that will be class 0. So we can do it outside of this particular thing. We don't need to be honest over here, so we'll just get rid of it. So we are having prediction scores as an empty array of the shape y dot shape 0, which is nothing but the 1500 values that we are having. So we are having the prediction scores over here, and the data type is basically the object. And object basically means, see, we are creating this empty array in order to replace these values with some actual value. So that's why we're just creating the data type as object. However, it's just going to get replaced with the actual values of the probability that we'll be creating. So let's just move ahead now. We are performing the stratified k-fold over here with the splits that we'll be defining by the num folds. The shuffle equals to true means the x values that we are having, the x arrays that we are having, we are just shuffling them. It's just going to help us overcome the idea of the overfitting. And the random state is again fixed as the random seed that we are having over there, that we are defined as 1. Right? Yeah, over here. So now what we are doing is, for the train index and validation index in kf.split. Now what is this kf? Kf is this object that we have created, and then we are using dot split over there, and we are saying x and y is the input that's going to take. So now it's breaking this x into the training part and y into the validation part. It's basically the index for the training and the validation. So now we are going to use this index of from this kf.split to get the training and the validation for each split that we are trying to create. So training index is going to give you the x train part, and the validation index is going to give you the x validation part. Similarly, this y train index is going to give us the y train part. And then see, we are having one of the factors of while we are training the classifier or the CNN model, we are having this one element as the class weight. Now it's going to make sure that we are giving more priority towards the minor class as compared to the majority of the class. And that's how we do it with the help of this class weight. And that's how we are distributing 0 as 505 divided by 1500, and 1 as 9 and 5 as divided by 1500. So that's what we are going to deal with, so that as I mentioned, the minority class will be given more weight as compared to the majority of the class. And yes, we are just simply going ahead and training the data for x train and y train. And remember, we are having 3 different splits. So if we are using 10 epochs, so 10 epochs is going to be repeated for 3 times, because we are having 3 different splits of the data. So total of there will be 30 times this whole process is going to go. And yeah, that's what we are doing in the training part. And then once we are getting the output of the training, what we are doing is, we are using the x validation that we had created and generating the y value of the prediction. Okay, and then after doing this, what we are doing is, we are just using this prediction underscore scores with the validation index. Wherever we are having the validation index, we are simply passing the outputs of this predictions of the probabilities of the y value. So that's how we are creating this basic function, or where we are checking the performance of our CNN model with the help of stratified cross validation technique. And then in order to call this function, obviously we are creating 3 different split, as I mentioned. The random seed, we are fixing it to 1. And after that, we are just creating the, or building the CNN model or the classifier that we are going to pass inside this function that we had created. And this summary is going to be used just to see, like, how the shapes are changing, what are the amount of parameters for each and every layers that we have created inside the CNN. And then we are just generating the probabilities for the y hat. And let's see what we are going to get after this. So first of all, over here we are having the model summary, and inside the model summary we had started with the shape of 101 cross 101 cross 3, and then we are using 32 filters. So the number of filters will add that much amount of depthness or the depth to your output of the image, and therefore it will now have 32 channels, and that's how we got 32. And I say that while we do the convolution part, if the padding is not the right, basically if the padding is not kept as same, which means that the output image should also have the same dimension as the input image. We did not do that kind of step, and that's why we are having this step, like the output basically is basically smaller as compared to the input that we are having of 101. It has been changed to 99. and the number of parameters for that respective layers were 896. So yeah, that's basically the summary. Again, the whole detail, if you want how, like what exactly or how exactly the summary are read, you can again refer to that same project that I told you earlier of the ship detection using the satellite imaging. So yes, I would again definitely recommend that whole project, because as I mentioned, right, I've explained almost everything in detail about everything related to serial and everything over there. So yes, do give it a watch once this particular video is over. And now let's just move ahead and see the overall history of the training. And because we know that the data has been splitted ahead into three different parts. So for each split, we'll have 10 epochs. So total there will be 30 epochs. So first 10 is over here. The another 10 is over here. Then the next 10, the remaining last 10 is over here. And you are seeing that almost every time we are getting the accuracy of 100. But now just remember that accuracy is not a good measure when we are dealing with the imbalance in the data set, because it's going to favor more towards the category which is more in amount. So for example, 0 over here. So because we are going to predict 0 in more ways compared to 1, you will just look into whatever I'm saying right now. You will be able to understand it when we'll be looking into the confusion matrix or the true positives, false positives, and all that kind of stuff. So just note that one thing, that the accuracy is not considered as a good measure, because it favors more towards the zero wala part. Why zero part? Because as I mentioned, right, it's the large amount present in our data set as compared to the target one or the class one. So yeah, it won't even show you how bad your model is performing while looking at the data set of classes or the targets one. Okay, so let's now move ahead, and obviously if it's not making sense to you, it's completely fine. I'll tell you what I exactly mean while we are looking into the confusion matrix part. So now let us look into the true positives, false positives, and true negatives. Basically, what we are doing over here is we are actually looking into how uh, wrongly our model has predicted the class 1 or class 0. We'll look into it in much more visualization fashion while we are computing the or visualizing the confusion matrix. But over here, we are just creating this particular code cell in order to visualize the images, like which are all the unique image IDs that we are having, which we have predicted incorrectly if the class was 0 or if the class was 1, and how many we have predicted it correctly. So that's what we are doing it over here. Starting with, we are creating a data frame again where we are just reading the training labels.csv file that we are having, which contain two only columns, like the only two columns were IDs and the labels. And now we are adding the third column to it, that is the predicted class. So now this predicted class is going to contain the value of either 0 and 1 depending on how the model is predicting, depending on the convolution that it has gone through. And after that, like how, like what exactly, like how are we converting the values of the probabilities into 0 and 1 is with the help of this threshold 0.5 that we are setting. So anything that is going to become greater than 0.5, any value of the probability in the prediction is, if it's greater than 0.5, will assign the value of 1, or it will assign the value of 0. So now that's what the prediction class is going to contain, either zeros and ones. And now depending on that, we are again going to compute the false negative, false positive, true positive, and the I should write over here true negative, not TN. All right. So now over here, with the help of this data frame that we have created, what we are saying is, get me the values of the IDs where your model is falsely predicting negatives, falsely predicting positives, or correctly predicting positives and correctly predicting the negatives, where negatives basically means the class 0 and positive basically means the class 1. So when we are having our predicted score as 0, but the actual label was 1, so what we are doing is we are incorrectly predicting, even though the label was 1 but your model is giving 0, and hence we are saying false negative is what we are collecting. So now I want all the IDs of the images in which I got false negatives. Similarly for the false positives, all the image IDs I want where my model predicted the class was positive but actually it was not positive, it was negative, and that's why we are calling it as a false negative, I mean false positive. And then if we move on towards the true positive and true negative, over here our model predicted 1 correctly when the label was again 1. So that's why, because it is positives is what we are talking about, so we are talking about true positives. True as in we predicted it correctly. And similarly for the negative, true negative basically means when our model is predicting 0 when actually the label was 0. So we are going to get all the values of the image IDs inside this fn, fp, tp, and tn. Okay, that's the thing that we are going to collect. And then now we're just going to create a function to visualize all of these true positives, true negatives, false positives, and false negatives. As in all the image IDs that we have collected, we are just going to visualize some of the image out of it to just know how, how it works. So yeah, let's go ahead and do that. So in this, we are defining the function named as show underscore images, where it takes the image IDs of basically this false negatives, false positives, or all the other stuff, and the number of the images that I want to display. So if I want to display 5 images, I would write the value of 5. Then what is the title that I want to give it to it, and what is the color that I want to give. So I'll just give red color whenever we have incorrectly predicted something, and green color when we have correctly predicted something. So I'm using this RC params from the PyLabs to adjust the figure size. Again, if you don't want to do that, you can directly use the plt.figure with the fig size. It's just another alternate way to give your figure a size. And then in order to get different index where we want to create our subplots, I am using the value of n as 1, starting it from 1. So I'll start from 1 and I'll always increment once the for loop is completed. So the next time my image that will be plotted will be in the second index, then the third index, so on and so forth, until the number of images that I want to plot for that respective true positives, true negatives, or whatever is the thing that I'm choosing. So what I'm saying is, I'm creating the for loop, and the value will start from 0 all the way up to the image I have selected. So if I'm saying 6 images, so it will take the image IDs from 0 to 5. So that's a total of 6 images will be there. And then I'm just creating the subplot, and I'm just having one row with different images plotted in that single row. And the index value, as I mentioned, is what I've been taking as n. And then I'm just showing that particular array with its respective index from 0 to whatever the values that we want to display. And the image, the size of the image is going to be same, so I'm just using the colon. That's the notation that we use in Python. So that's how I'm going to display that particular image that I want to show. And then the title that I'm giving over here is the image ID and the value that I'm having. So if I'm starting from 0, the value will be 0, like that. So that's what I'm basically choosing. And then I'm just keeping the axis off. I'm just turning off all the axes so that I'm not giving any kind of marks on the axis, then values of the pixels, and what are the total number of pixels and all that kind of stuff. So it's, I don't want to do that, so I don't want to see that, and hence I'm keeping the axis as off. And then I'm giving the subtitle. So what is the subtitle? It's going to take the title, as in over here, see, I'm describing the title as the title of the subplot is called as the subtitle. I'm giving it on the top, and hence we call it as a subtitle. So examples of true positives, where we are predicting the solar panels if they were present. So correctly we are predicting the solar panel, so it becomes true positive. So that's what I'm giving the multiple different titles for each subplot that we are going to create. And yeah, that's all about it. That's pretty much about it. Like the number of images that we're going to pass in all the things that we are going to define as 7. So we are going to look at total of 7 different images for false positive, false negative, true positive, and true negative. And yeah, then we are just again using this plt.show to avoid any kind of writings of the title or any kind of position of the title and all that kind of stuff by using this plt.show. And then I'm calling this for 4 different times. Once for the true positive. Remember, true positive is containing all the values of the image IDs that was correctly predicted if there was any kind of solar panels present in the image. So all that image IDs are now from like the first image ID till the 7th image ID. I'm just going to visualize it, and see, this is the kind of thing that we are having as the display. So image ID 2, 3, 4, 16, 17, 26, 30 were having actually the solar panels, and our model also predicted that they are having the solar panels, and that's why it becomes true positive. And as we can, there are solar panels over here, here, and for this image over here. Similarly, we'll be also getting the plots for the false positives, true negatives, and false negatives. So let me just again take one example of false positives, which basically means that our model is predicting solar panels even if they were not present. So over here in this image, there is no solar panels. Over here also there is no solar panels. Similarly over here, here, and over here, there are no solar panels, but still there are some kind of features based on which our model is predicting that it must have some kind of solar panels. So that is what is called the false positives, and these are the image IDs that we are visualizing, the first 7 image IDs. 1, 2, 3, 4, 5, 6. There are only 6 in this case. So it basically means we are only having false positives of 6. We are not having more than 6. So you are also going to visualize this while we are going to compute the confusion matrix at the end. Let me quickly show you where it is. Yes, see, we are incorrectly predicting this thing for 6 times, and that's why we are only having the output of 6 instead of 7. So that's the basic thing that we are seeing over here. And similarly for the true negatives, there were no any kind of solar panels and we are not predicting any of it. And for the false negatives, we are predicting that there are solar panels even if they were not. So like, or I said it incorrectly. We are predicting no solar panels even if they were present. So over here we can see that the present, like the images were containing the solar panels, right? Images were containing the solar panels, but our model predicted that there will be no solar panels in these images. So yeah, this is a very quick visualization of all these true positives in order to give you some kind of a sense of what all these kind of things mean. And now moving on towards the evaluation of the model and the results. So let us go ahead and first of all understand the ROC curve, because that's what we are going to plot the first in the model evaluation part. So in this ROC curve, we are basically plotting the true positive rate against the false positive rate, where true positive rate is nothing but how many times our model is correctly predicting the positives out of the total positives available. And similarly for the false positive rate, how many times our model is predicting positive when it was negative out of the total negatives. And now the basic idea, the basic understanding or the common logic that supports this whole graph will be, the more your graph is towards the true positive rate, the better your model has classified. So I'll just go ahead and you can just go ahead and read through all these kind of things. So basically, because we are talking about the rate, the values will stay in between 0% and the 100%, that is 0 to 1. So now if I just show you the graphs of this very quickly. So over here we can see that the false positive rate is going from 0 to 1, as well as true positive rate is going from 0 to 1. Now more and more towards your, like more and more your graph goes towards to this particular part, the better area under the curve is what you will be getting. So if the area under the curve is closer to 1, your model is just fantastic. And if it's less than 0.5, see, 0.5 is the chance is in any kind of random classifier will give you the output of 0.5 AUC, any random, okay. But the good classifiers will give you the values that is greater than 0.5, and it is better if you go closer towards the 1. And if similarly it's not good if you are going away from that 0.5 towards the 0 side. So that's the basic idea of the ROC curve, and we have got the area under the curve for for this particular model as 87%. So this is the 87%. So that's we are going, like the inclination of this curve is more towards the true positive rate, so that's good. And now we just remember we have used only 3 folds, and and that we can obviously increase that split and look at the output that we are getting. Also for each split we have just trained them for 10 epochs, so you can try to increase it to, let's say, 40 epochs, 50 epochs, and see what is the overall output we are getting at the time. So for sure this value you can increase from 87 to more like closer towards the 99 kind of thing. But yeah, that's the overall idea of what is the ROC. And this is just a basic version of plotting that we are using with the help of matplotlib, where we are computing the false positive rate and the true positive rate with the help of the ROC curve. This is the matrix that we have imported from the sklearn matrix, and we are just passing in the true positives, the true values or the actual values of the y and the predicted values of the y that we got from the CNN, and we are getting the respective false positive rate and the true positive rate. And after that we are getting the ROC AUC curve. Basically this is giving you the value of the AUC, and because we want to show this on in the legend of the plot, and that's why we are saying the legend string, like the legend that we are going to use is the legend string while plotting this graph, and which says that CNN model with the AUC score of, like, I want the answer correct to the 3 significant figures. And if you would have noticed, it's 870. That's the 3 significant figures, the value that we are getting. And I'm just passing that dot format to give me that 3 significant figure output of that AUC value. And then I'm just simply plotting this x-axis, the false positive rate, on the y-axis true positive rate. I'm giving the red color to this line, and giving the label as this particular string that we had computed. And then this is the chance that what is the random predictor or the classifier would give you the output, that is 0.5. That's always what we sketch. And then we're just customizing our plot, giving some X label and all that stuff. All right. And here is the graph that we are having for the ROC curve. So let us now talk about the confusion matrix. So confusion matrix, I have been talking about it for quite a while now. So it basically is taking the actual part, or like the actual, what is the actual label of the images and what are the ones that has been predicted by our model for that particular image. So this negative and positive are nothing but the respectively 0 and 1. And so if my model is predicting 0 and actual value is also 0, so my model is correctly predicting that negatives. So it becomes true negative. Similarly, for false positive, false negative, and true positive, so these are actually the values which tell us how many times your model was predicting correctly or incorrectly for the respective class. So this becomes really very good while visualizing it. So over here, see, my model is predicting. See, if you remember, we were having 995 values with the class 0 and 505 values with the class of 1. So let's say these are the actual values and these are the predicted values. So if the value of 0 actually was 995, so out of that 995 my model has predicted 989 of this uh, images with no solar panel. So that's a pretty impressive thing, and only 6 images out of it have been predicted incorrectly. Similarly, now if you look for the class 1, for the minority class, now see the minority class, because it was minority, so now we are actually saying that the amount of incorrect predictions, like when the image was having a solar panel but my model is predicting 0, no, it is not having solar panel. So this incorrect predictions over here, the false negative, is very much high. So this is not what we get to see in the accuracy. Our accuracy was pretty much high. It does not tell you this thing that wait, for the minority class the incorrect predictions are pretty much high as compared to the this particular predictions. So now that's the idea. Like this is the majority class of the overall predictions that went incorrect is less as compared to this, and we can only get this better idea with either the ROC curve or the recall or the precision or the F1 score, or maybe with the help of the confusion matrix where you exactly know how many values have been predicted correctly or incorrectly. So yeah, now what should be our goal? Our goal should be to decrease this as much as possible. Now that's something that you need to think about how you can do it. I would recommend that you take whenever you are doing the augmentation of the images, you try to pick up all the values with the class 1 and you augment that and increase the values of this labels one, and then you will be seeing significant drop of this particular value. And that's one thing that you can try, and obviously you can try some multiple different things based on your research. But yeah, one of the tasks for you is to decrease this value as much as possible, where your model is incorrectly predicting the negatives. Whenever there was a solar panel, your model is giving no, there are no solar panels, so you need to decrease this value. So these are basically the tasks for you that I have already mentioned. You are going to use the data augmentation to increase the size of the training data. And then if you are familiar with the transfer learning technique, so transfer learning is a technique where we are using the pre-built models and taking the parameters from, we are taking the saved parameters from them and implementing it into our use case. And then we are going to see if we are going to get the better outputs or not. That's one more technique that you can use, obviously, that is the transfer learning, only if you know about it. And if you don't know about it, you can do a quick research on it. It's a pretty straightforward thing. One or two searches will give you a very good resource through which you can learn this transfer learning technique. And in either of the cases, whatever you're going to use, what is your conclusion based on what are the steps that you have performed? Okay, now this is only one task. This is not multiple tasks that we are giving. We are just giving you one single task where you're going to perform this data augmentation. And if you are familiar with the transfer learning, you are going to implement it, or just try to research and try to implement if you can. But no matter whatever the thing that you're going to do out of this two, you are going to give your conclusion based on what are the things that you have changed and how you have tried it. And then you can simply click on this particular link. It's going to redirect you to the Google form. And once the task is done, we'll go through it. Our team is going to go through it and then give you the certificate based on the email ID that you are going to provide. And all the information over here should be pretty much accurate. How you can find out the project ID and the project name, you can just scroll on the top of this particular file. Okay, I'll just zoom out. If I just go on the top over here, you are able to find this project ID as well as the project name. You can just simply copy paste it over here. Then provide your full name, your email ID on which you will be getting the certificate, the phone number, the LinkedIn profile, and if you all the task or not, or like, yes, as in you completely solved it. No basically means you have tried it, but yeah, the overall output that you are getting was something that you are submitting. All right. And the submission file, the overall notebook with the changes that we had asked you to do. And if you would like to get notified, you just fill in all these details, subscribe our YouTube channel if you haven't already. And you can see, the one thing that you need to keep in mind is you first of all need to create your account into our Spartificial website if you haven't already. And once you are done completing this process of the sign up, once you are at the basic idea, the fastest way is to continue with the Google account. The Google account that you're having, you just link it with it, and within just few seconds you will be getting your account ready in the domain of the Spartificial. Basically, you will be having your account with the registered with the Spartificial. So once this is done, only then we'll be going ahead and looking into your thing that you have done for the submission part. And after that, you also, if you haven't yet subscribed our YouTube channel, please do that if you are liking that work that we are providing the help of YouTube. But anyway, with that being said, we are done for this project, and you can just write some comments based on how you felt on the overall project. If you are having any kind of doubts, you can just comment it out, and our team is going to help you as soon as possible. So yes, do drop a like, do subscribe if you haven't already, and do share it ahead with your friends. And I'll see you again with some exciting project very soon. Stay tuned. Future research should examine the use of supervised learning techniques to not only identify the existence or absence of solar PV, but also to estimate the energy consumption associated with each installation. This could be achieved by integrating other data sources such as geographic data and energy usage patterns. Ultimately, increasingly accurate information around both consumer solar adoption and solar energy consumption would aid policymakers in the structuring of new green policies and incentive programs.